Good morning. It's Monday, the 14th of December, 2020. And we're still here. Still managed to get my 2 stars every day. So I don't think I'm gonna go all the way to Christmas, to be honest. Just gonna put that out there so people aren't disappointed. I'm taking a well-deserved 2-week break after this week, and I don't think I want to be coding every day after that. So, but we're gonna see if we can make it at least to the end of this week. We got a new puzzle. Haven't checked it out yet. I do want to briefly revisit. Hey, you saw that? I set up, finally set up OBS to switch scenes when I switch to Emacs or to my terminal. So that I don't start coding without anyone seeing what I'm doing. So yesterday on the stream, I failed to get part 2 and didn't really want to spend too much more time on it live on air. But then I stepped away, took a break. Sometimes the best thing to do in programming is just take a good break. And then I came back to it and finished it without too much more effort. So this was our original approach for part 2, where we sort of have, the cycle generated by one bus. So this is a sequence based on iterate, where we just iterate and add numbers. And then we use a filter to narrow that down to only the numbers that also match the other bus, so that we can sort of combine these different buses and build up ever more coarse-grained sequences. And this is my new approach. And so this turned out to be way too slow. It worked fine, until for 5, 6 buses, but we had 8 to go or 9 to go, and then after that it just exponentially started going up, and it probably would have taken years to finish with 9 buses. So this is the new approach, and what's the difference? So here we're still doing the same thing. This is really the code that we had above there. But then there's a key insight, namely that this new sequence, this new cycle, it's still a cycle. It's still gonna repeat. I think there's people posted all kind of mad stuff, but there's also a good analog, I think, from physics. If you take two waves and you add them together, or you multiply them, you're gonna get a new wave with a fixed wavelength. There's eventually the pattern is gonna repeat. Eventually they're gonna come back to 0, 0, and it's gonna repeat. So if we just take 2 numbers from this new sequence and then start a new sequence based on that new offset, that new difference between two parts in that cycle, we're basically doing the same thing as before, but we're just skipping so much of intermediate computing, so we basically start hopping over ever bigger intervals. And that did it, 0.4 milliseconds to compute a fairly large number. So I was happy about that. All I'll say about that. Yeah, so people pointed out there's and I didn't have a chance to really have a good look at it, but it's often like that with advent of code, right? Where it's like somebody links to a specific Wikipedia article, to a specific algorithm, and they're like, okay, well, you can solve it with this, and if you know that, then it's basically trivial. It's like a straightforward application. And I've said this before, like I often have the feeling with advent of code that they actually work their way back, right? They kind of start from interesting algorithms, interesting mathematical applications, and then sort of try to phrase a puzzle around that. And I guess that's not bad. It does sort of expose you to these different ideas, but it does mean that if you sort of try to solve it from first principles, yeah, you might be in for a serious challenge. And while I can see the benefit of, being exposed to these different ideas, like you never know, like when you run into a similar problem, and now you have that sort of as your part of your toolkit. At the same time, I don't know, I can't say that any of these algorithms or principles that I learned from Advent of Code have ever been useful in my job. I mean, it depends what you're doing. Maybe if you're more into, numerical stuff, machine learning, maybe, I don't know. But okay, you know, like they're puzzles. We do need to have fun as well. So let's see what we have today. Day 14, docking data. As your ferry approaches the seaport, the captain asks for your help again. The computer system that runs this port isn't compatible with the docking program on the ferry, so the docking parameters aren't being correctly initialized in the docking program's memory. After a brief inspection, you discover that the seaport's computer system uses a strange Bitmask system in its initialization program. Although you don't have the correct decoder chip handy, you can emulate it in software. The initialization program, your puzzle input, can either update the Bitmask or write a value to memory. Values and memory addresses are both 32-bit unsigned integers. For example, ignoring Bitmask for a moment, a line like mem811 would write the value 11 to memory address 8. Sure. The Bitmask is always given as a string of 36 bits, written with the most significant bit on the left. Makes sense, and the least significant bit on the right. The current bitmask is applied to values immediately before they are written to memory. A 0 or 1 overwrites the corresponding bit in the value, while an X leaves the bit in the value unchanged. Okay, so let me also get a bit of a sense of what we're actually looking at. Right, so we kind of have two types of instructions in a sense. Either it updates the bitmasks that's currently active, or it sets a memory address. And how are those two related? Oh, the bitmask changes the written values. By expanding everything out to individual bits, the mask is applied as follows: value, mask, result. Yeah, sure. So I can already see. So, I mean, applying a bit mask to a value, we have several options for that, and or XOR. But it's kind of none of those, right? It's like it's an AND with the zeros and an OR with the ones, because we really just sort of want to overwrite specific positions. Instead, then the program tries to write 101 to address 7. Yeah, I think I get it. What is the sum of all values left in memory after it completes? Okie doke. Demo input. Let's get started. Yeah, let's just. And then can we use our existing util function? Are we resource seek? Yeah, we can use that, but first we're gonna have to do it on this one. So let's see if we do an reseek. Yeah, and here we do that also on the line seek. Yeah, so we're gonna do a string split lines of the demo input, and then actually map over an refind. giving it a regular expression, word plus, start with that, so missing, no, still doesn't like it, split lines, add missing, there you go. Yes, so that's the instruction. Then optionally, we have, and we need to quote or escape these digit plus. No. And actually, okay, maybe I'll group this one as well, so we already have that for parsing. Equals whatever else is there. Mem 811 mask nil nil the mask yo. Sounds good. I'm gonna make a helper function for this as well. Re string seek string s. So we sort of have both of these, like one that we can do on a string in the source and one of them that we can do on a file. Clojure string as string. And yeah, let's do the same thing that we do over there. Drop that first match. So that should mean that we can do a util re string seek on our input. Cool. Hey Samir, nice to see someone on the chat. I mean, it's Monday, people have stuff to do. It's pretty quiet today on the stream, but that's cool. It's nice to see you. And yeah, of course the video will go live after. Yeah, and then let's map over this, or let's just do a for, even though we can just straightforwardly destructure that, or let's say operation. We don't need that one. This one is the address, and this one is the value. Does that make sense? Op address value. Yes. And then let's say case op. If it's a mask op, we'll just go and return mask value. I think we may parse that value some more, but let's start with this. And then if it's a mem, we can say mem read string address read string val. You can see as the week goes on that I kind of get lazier and use this read string more, which Vincent, who just dropped into the chat, pointed out to me 2 weeks back, I guess, that read string is a pretty decent parser sometimes. So that's our input. Now these masks, I feel like I want to, so we have this mask here, and I think, you know, processing the mask is really what it all comes down to here. And I think I want to split this into two separate bit masks. So if we have this, if we can build up one bit mask that looks like this, and one bit mask that looks like this, right? So like one is all zeros except where there are ones, and one is all ones except where there are zeros. Then we can say or, you know, bit or this one, and also bit and this one, and then we set all the numbers. 36 bits they said, right? Yes. Does that mean we need a big int? It probably does, huh? How big is this? And is that... No, that still fits in along. Are longs 64-bit? I guess they are. I should know this stuff. Yeah, all right. Well then. Yeah, and let's again, I mean, in a previous puzzle, I kind of, you know, did this proper parsing with bit shifting and stuff. Not gonna bother this time. Instead, in that previous exercise, someone pointed out string escape. So let's say we have this thing and we replace x's with what do we want? We want either this or this, right? So if we replace x's with zeros, values are quite small for long as well. I think it worked fine for me to be. I mean, most of Clojure's math operations are checked, right? So it would know to. Plus Clojure by default, you know, pretty much all Clojure math operations are gonna give you a long, even if you. So I'm pretty sure, like, you know, if we add two ints together, that's still gonna give us a long. That's just how Clojure works. You don't really get ints in Clojure. You can explicitly cast to an int if you really want something to be an int, but for the rest, everything in Clojure uses floats. Uses longs and doubles. For floats, it's kind of similar story. They don't bother with the regular float. It's double all the way. So that's one, and then for the other one, we want to turn x's into ones. Yeah, easy peasy. And then if we say read string of string to our this thing, we get a number, which in this case is 64, which makes sense. 1, 2, 4, 8, 16, 32, 64. Let's give that a name. Defin parse bitmask mask. What do we call this? Bit, whatever. Oh, not a. No, that's not what I wanted. Yeah, thread lost also looks weird. No, this is not too bad. If I put this here, then that looks okay. So escape the mask by replacing x's with the bit. Put 2r in front so that Clojure knows that it's a binary number, and call read string on it. and that means that we can here parse this to a tuple. Well, let's just put them both in here. Parse bitmask value 0 and value 1. How does that look? Yeah. Yeah, and now I think it should become fairly straightforward. Gonna do something similar, so dev instructions. Well, let's also, okay, let's dev parse instructions, Stefan input form occurs an even number of forms. Yeah, oh, okay, yes, input. So that way we can say parse instructions, and let's call this something def pattern pattern, and for the real ones we can say, wait, util, yes, re, there we are, resource seek for day 14 and the given pattern. So def demo def real. Cool, cool. And then let's say apply mask. Let's do that separately too. We have a number, and then I don't know if I, no, I'm just gonna 0, 1. And that's basically just bit or the number with the pattern of the zeros. No, is that, yeah, because no, we wanna, well, it's actually, no, it's actually, so, okay, here we did the parse mid mask, replacing it with zeros, which means that the ones are left. I'm gonna flip this around. I think that makes more sense. So here in this case, this is 64, right? Like this is they're just a single one in there, and that's the one we wanna set. So we do a bit or. Whereas this one is mostly ones, but there's a couple zeros in there. So we say bit and this second one. All right, loop. Let's start with an empty. Oh yeah, and the mask we need to apply. Starts by specifying a bit mask. The mask specifies will override 2 bits in every, yeah. And then if you have a future mask, it changes. Just does it just reset the mask, or does it apply itself to the mask? No, it just sets it, I think, right? So well, actually, let's do a reduce. Yeah, with this as well. Just put it all in the same map. We can do that, right? Like so we have our, well, let's say demo. So this is just a map that's sort of holding our memory addresses. This is our instruction where we have op v1, v2, and in case op, if it's a mask, then we recur. No, we don't recur. We just return because this is a reduce. We just say assoc mem mask. Well, let's say mask 0, mask 1, mask 0, v1, mask 1, v2. Whereas if it's a set memory, then we assoc mem the number with apply mask the v2 mask 0 mask 1. What does that look like? What's that doing here? Yeah. Okay. So to initialize your first, yeah, you need the sum of all values left in memory after, yeah, the entire is only two values in memory are not 0, 101 at address 7 and 64 at address 8. That's what we have, producing a sum of 165. So then part 1 input and then when we're done with this, we say dissoc mask 0 mask 1. We don't care about those anymore, so we just get all the numbers in there, values, and then reduce plus. Just need to make sure. So in the past I would have written this as apply plus, because they're definitely like you want to do apply concat, you never ever want to do reduce concat. We talked about that in the past, how like concat build up these lazy sequences. And so it's a kind of a pattern where these multi-arity functions in Clojure core often perform better if you pass in stuff across all the arities instead of doing reduce over them. But I tried it out on plus because I saw someone else do reduce plus recently on an event of code solution, and reduce plus actually seems to perform a little better than apply plus. I don't know, or maybe my micro benchmarking was a bit off, but it doesn't seem to perform much worse in any case. So let's see, demo is 165. Okay, and if we do this on the real stuff, we have a large-ish number. And so far so good. All right, now how hard does it get? Okay, version 2 acts as a memory address decoder. Immediately before a value is written to memory, each bit in the bitmask modifies the corresponding bit of the destination. If the bitmask bit is 0, the corresponding memory address bit is unchanged. If the bitmask bit is 1, the corresponding memory address bit is overwritten with 1. If the bitmask bit is x, the corresponding memory address bit is floating. Okay, oh boy. So it kind of combinatorial thing again. So everywhere where it's an X, we kind of need to go over all the different possibilities. Consider the following program. When this program goes to write to memory address 42, it first applies the bitmask. Address mask result. After applying the mask, 4 bits are overwritten, 3 of which are different, and 2 of which are floating. Yeah. Right. How big is our input? 565. I'm just gonna do this relatively naive and see how far we get with that. I think this is still fairly doable, but we're gonna have to re-architect some of our parsing. I mean, pretty much all of this. Let's see. Let's start with this. No, this one actually, so this is still fine because we still want to set the zeros and the ones. But then we need every single combination of the x's. And it's kind of same thing where we want to both set zeros and ones. Okay, first of all, this bit or bit and stuff. Can I write this in a smarter way so that we don't have to encode these separately? No, it's kind of a tri-value logic. Yeah, we do need these different cases. So yeah, let's take this as example. Yeah, let's also let's copy this. Dev demo 2. Or what do we call it? Input 2. And so in particular, this mask. Okay, I guess I can. So parse Bitmask. We had this part. And I think I'm just gonna keep that, but then write a second procedure. Say we reduce this. cases here, 0, 1, x. 0 and 1 we kind of ignore. Actually, maybe. How about? How about we start with these? So this is the number that's going to be like 1, 2, 4, which actually means I need to multiply this by 2. Same for these. Multiply this by 2. And here, still kind of same thing. Multiply that by 2, but now we're going to map cat over these results. Each of these are pairs, zeros, ones. Yeah, right, because like the first one, yeah, the zeros are I'm confusing myself with these zeros and ones, huh? So parse bitmask. These need to be ANDed and these needs to be ORed. Alright. Yes. Gonna call this ANDmask and ORmask thing. That makes more sense. And for each of the ones that we have, we're gonna add 2 okay, so let's say let's XX1, I don't know. So we have this 7, 1. And that's what here ANDmask and ORmask is going to be. And then we get to this X. So our pulse is 2. And so in the first one, I guess we want to, in both of them, so does this make sense if I say that we get bit and bit or and mask pause. bit and or mask plus the original. No, it can't be both. No. It needs to be, I guess it needs to be like this. Does that make sense? Oh, wait. Crap. It's not bit or, it's bit and bit x or I don't know what I'm doing. How do you print? It's like, can you say to string 72? No. Java print binary format integer to string to binary. Oh, to binary string. Is that a thing? Yeah, for integer, but not for long. Really? That? No. What are you? Oh, it's a static. Really? Does long have it? Oh, yes, it does. Okay, cool. Just so we can visualize this stuff a bit. Clojure walk as walk. Let's see. Walk post walk nums if number belong to binary string, else just the thing. Key must be integer. Function comes first. Okay. And what do we say our input is? XX1. So we're first gonna not change the first one because these are the and or yeah, and this is definitely so what we would expect to see. What do we want to see? That's correct. That's where we started from. That's our original Bitmasks. But then we also want to and 0, 0, 1, because these can also set things to 0. But we also want to set them to 1. Am I making it too hard for myself? Am I just confusing myself? How about we take a different approach instead of with these two different numbers, which we and then or I feel like this is too confusing. Is there a better way? I mean, the issue is that it's ternary logic, right? So it's kind of hard to encode it in a single number because we don't know if we want to set a bit to 0, set it to 1, or leave it alone. So that's why I'm encoding it in two numbers. Of course, we can continue to encode it in this kind of string or some other sequential data structure where we have 3 values, but then we kind of lose the elegance and the speed of these binary operations. So no, maybe I will just stick to what I have, but let's look at this example. So this is the mask. So given this mask, after applying the mask, 4 bits are overwritten. So because there are 2 x's in there, we want to see, keep it a string, forget the speed. But it's not just the speed. I don't like it. It's ugly. Let me give me 5 more minutes to see what I can do with this. How many are there? 6 here. 6, 3x, yes. Yeah, so 0, 0, 1, 1, 0, 1, 0, 1. Yeah, so this is just sort of binary looping over this stuff. I think I can make this a little easier on myself if I make a little helper where I say set bit, and then this takes the pair and mask or mask. Let's just, let's just split this up. Position bit. If you want to set a given bit to 0, then that means that you need to AND with 0. And so that means that that position in the AND mask needs to be 0. So how do I set? I mean, yeah, that's what I was doing before, right? Like, if I say bit XOR long max value position, that should give me it's also bin string and long to binary string n. So let's say I do a bit XOR with 4. Yeah, then I have all ones except at position 4. And then when I bit AND this into my AND mask, Now I have set that bit to 0. It's probably a better way to do this. Bit or mask, and so in this case, yeah, I just that's straightforward. Just gonna set this. So I feel like this is already gonna make this a little easier, because now I can just say, you know, pair. And so given a certain position, we want to have the original pair, because we want, plus we want to set that bit to 0, plus we want to set that bit to 1. One, two, three, pair. So where's my walk? And let's also maybe pad this. Can I pad this with zeros? Can you pad a string with zeros? No, it doesn't like that. Okay, whatever. Forget the leading zeros. What does this yield? Whoa, wait a second. Here, we're updating the and mask. The or mask stays the same. We're updating the or mask. The and mask stays the same. No, come on. So let's do that on this demo input they have here. How is it? Mask. What was I doing here? This is my original part 2 solution, or attempt at. Gonna move this down, see if we still do something with that or not. I know I'm probably making it harder for myself than it needs to be, but I feel like I've got some sunken cost fallacy going on here. But I do think we're gonna make it this way. So if I parse pair this thing, and then yeah, let's say yeah, let's actually go back to our reduce. So here, this is what I want here, pair. Parse pair mask. Say that this is the mask. Pair. Yeah, and so what I have here, right? 2YL. And reverse. Okay. I say first, and then where's my walk? String tree. One, two, three, 4, 5, 6, 7, 8, 9. Are there duplicates in there? Distinct. Do I not want this? Now I got 4. Looks okay-ish. Let's see. So 1001 is kind of the middle pattern. We always want to set those. So the OR in this position is always 1, and this position is always 1. The OR and AND are both 0 here. Yeah, which is fine. And yeah, then we sort of have the binary combinations on all the other ones. I do just realize now, maybe we don't need that pairing at all. Are our pairs always identical? No. Oh, is it just because we don't have any leading? No. Okay, this is kind of weird. Why are they all identical? Okay, it doesn't matter. Let's try where we can get with this. Wait, I already had this one, right? Demo input 2. Let's put this here. Yeah, part 1, real, part 2, parse bitmask, part pair, set bitmask string. So in this case, our parse instruction bit. Yeah, this has not changed. So we need a new parse instructions. Expand mask. So this, given a mask, gives us pairs. Why are all these numbers the same? That doesn't really make sense, does it? 514. Is indeed 11. Does that make sense? Maybe just sort of accidentally ends up that way. If you have 001 and 101, let's just test it out. Let's just see what we get. So what I wanted to do basically is here say expand masks value. So parse instructions demo input 2. Oh, already over the hour. I hope this works. If this doesn't work, I'm out. No, is it address? It's just no, it has to be value. What does it say? Mask. Oh, does it have to be no, parse pair? No, we parse it. And not supported parse instructions. 98. What is it? Demo 2. No, just like that, like it's already parsed. And let's get rid of this boy, huh? What is still printing? Where do I still have a... Oh, over here. Let's say 2 though, right? And then yeah, this does blow up a little bit. Jesus Christ. And always these, yeah. Yeah, okay. I'm starting to lose confidence that this is actually gonna work. Let's try it. It probably won't, and then I'm just gonna call it a day there. Went a little bit into the woods with this one. Where's our original state machine? Masks. If then just assoc v1. If it's mem, then reduce masks over memory. Got the memory, got the mask, and we say assoc memory apply mask mask over v1 v2 dissoc masks let's start there. Part 2, demo 2. 6. Wait. Oh. Causing writes to 8 memory addresses. The entire 36 address space still begins initialized. In this example, the sum is 208. No, it's going to be higher. It's 408. Conspicuous. So we're talking about 42, yeah? So the address 42, it first applies to bitmask. After applying the mask, 4 bits are overwritten, 3 of which are different, 2 which are floating. Floating bits take on every possible addition of values. 4 actual memory addresses are written. 26, 27, 58, 59. We are not writing any of those. Okay. Yeah, I kind of wanted to see this approach to the end, but I think it's clear that this was not the best way to approach this. So I think I would have to go back to the drawing board. But that's more than enough time for today. Yeah, we'll see what tomorrow brings. Thanks a lot for watching.